welcome back to the Deep Dive. Our mission here is, well, it's to take your crucial source material, in this case, your amazing research, and give you a shortcut to mastering the narrative, especially in English.
And Zorka, today is all about you. We're focusing entirely on your work at Biosense Novi Sad. This is a special deep dive, part of the QPM Drive and English Initiative, all prepared by your teacher Miroslav.
That's right. We're going to be drilling down into your process for synthesizing nanomaterials. A lot of electrochemistry.
We've got your recent notes right here. I mean, all the prep work for your next big experiments, the papers you've read, the calculations, the critical decisions you've had to make.
And we want to look at not just the science, which is fascinating, but the language you use to communicate that science with, real precision.
Exactly. Think of this as taking all the rigor from your lab work and just translating it directly into clear, confident academic English.
Okay, so let's unpack this. The first thing that jumps out is just the sheer volume of preliminary work.
Oh.
You're reading, a large number of scientific papers, pulling out key data, putting it into your files, and then, boom, straight into preparing protocols.
That's not just a full work week. That's laying the entire foundation for the experiment to succeed or fail.
And the language used to describe it, I thought, was perfect. You said, in the past week, I had a lot to get done.
And that phrase is, it's just such good, practical, professional English.
Right. It immediately tells me about the effort involved, but also that you're managing it. It's not a complaint.
No, not at all. It's confirming your competency, your efficiency. You're handling it.
I can see how useful that would be in, say, an EU project update or talking to collaborators.
Absolutely. You can just say, I still have a lot to get done before the final experiment, or we realized we had a lot to get done before the project meeting. It sets a professional tone immediately.
So once you've done all that reading, all that data extraction, you move into the calculations.
Yeah.
From theory to action.
And you signal that shift with a very simple but very important phrase, after that.
And that phrase, after that, actually brings us to a quick linguistic point, a sound that can be a little tricky in English.
The short A sound. The A sound, you hear it in both of those words, after and that.
Yeah. It's about relaxing your jaw a bit.
Mm-hmm.
After that. Getting those little connecting words right makes everything else flow so much better.
And it pops up all over your field, Zorka. Think about words like ask, sample,
parameter,
catalyst. They all have that same A sound. It's a really good one to practice.
So after that literature review, you get to the core science in your notes, calculating the necessary parameters.
Right. Concentrations, potentials, everything you need to synthesize the materials, starting with the concentration of your precursors.
Okay, let's just pause on that word for a second. Precursor. It's a great technical term.
It is. And for pronunciation, we want to stress that first syllable. P-R-E,
That stress pattern helps everyone immediately grasp what you mean. The starting ingredient, essentially.
The chemical that comes before the final material. Exactly. So once you have those precursor concentrations, the real electrochemistry kicks in. And your big decision, the central question,
was about which electrical potentials would lead to synthesizing zinc oxide.
Rather than metallic zinc.
And here's where we really need to get into the details. Why is that choice, that specific distinction, so critical?
Well, it's everything. It's the difference between a working sensor and, frankly, a piece of junk. You're aiming for zinc oxide.
Because it's a stable, semiconducting nanomaterial.
Exactly. It has the catalytic properties you need. It can interact with the target molecules you're looking for, the pesticides.
So what happens if you get it wrong? If you push the potential too far and you end up with metallic zinc on your electrode?
Well, that's a disaster for a few reasons. First, metallic zinc is just not as stable. It'll oxidize and degrade the sensor.
Okay.
Second, it doesn't have the right electronic structure for what you need for the sensing application. And maybe the worst part, if the film of metallic zinc gets too thick, it's conductive, it could actually cause a micro short circuit right on the electrode.
Wow. So it would just completely destroy the whole mechanism.
Totally destroy it.
And that perfectly explains why the language you used, rather than, is so important. It's not just a style choice.
No, it's a high-stakes scientific decision. You're using that phrase to explicitly rule out the bad option.
It adds clarity to your reasoning. You're not just saying what you did, you're explaining what you avoided doing and why.
Precisely. And for writing protocols, Zorica, this is gold. You can say, we selected zinc oxide rather than metallic zinc due to its selectivity. It draws a very clear line.
Or even for planning, right? I'm focusing on optimization rather than initial synthesis right now.
It defines your objective perfectly.
And this precision is what led you to narrow it down to 3 specific potentials, minus 1.5 volts to 0.8 volts, which I have to say still seems like a quite wide window.
It is a wide window. And that just highlights the complexity here, because all the different research papers report slightly different conditions.
So your calculations get you in the ballpark.
Yeah.
Then you have to optimize.
You have to optimize. You're basically fighting against those competing chemical reactions in real time.
And you pointed out 3 key things that need to be adjusted at the same time: deposition time, the pH of the solution, and any additional agents.
And that's the real challenge, isn't it? They're not independent variables. They all interact. They can fight each other.
How so? Give us an example.
Well, you might find a high pH is great for depositing the oxide structure you want, but then trying to keep the whole system stable at that pH for a long time becomes incredibly difficult.
So when you have all these variables interacting, you need a very formal academic way to describe those dependencies.
Which is where your other phrase comes in, one that is absolutely essential for scientific writing. With respect to.
With respect to.
It's the formal way to signal that relationship. You're telling the reader, I'm defining the context for this variable.
So you don't just change the potential. You adjust the parameters with respect to the solution's pH.
Exactly. Or, for a bigger picture view, you might write in a report, this new method is more effective with respect to sensor stability.
It's precise. It's professional. Indispensable, really.
It really is.
Okay, let's get back to the physical experiment. All this deposition, it has to happen only on the working electrode.
Right. The other 2 electrodes, the counter and the reference, they have to be protected.
That sounds like a major engineering problem. You need some kind of semi-permeable membrane.
It is a problem. And this is where you use that wonderfully simple conversational English phrase. You said that part was tricky, too.
I love that. Tricky.
Yeah.
It perfectly captures the difficulty. It's complicated, but it also hints that you found a clever solution.
And the solution was clever. Finding a membrane, probably made of Nafion and other polymers, that creates a sort of mesh.
A mesh that lets the right things through, but blocks the deposition.
It has to let the right ions pass through to complete the electrical circuit, but physically block the zinc oxide from coating everything else. It's a filtration and an electrical balancing act all at once.
And it's so natural to share that challenge with a colleague by just saying, yeah, finding the right membrane was tricky.
Or optimizing the agent concentration can be tricky. It's honest and clear.
So this whole process, from the math to the tricky membranes, it all revolves around one main instrument, the one doing the electrochemical deposition.
The potentiostat.
The potentiostat, absolutely. Yeah. And since we're talking about mastering English for conferences and presentations,
we should definitely focus on pronouncing these long technical words clearly. It helps the audience focus on your science, not stumble on the sounds.
Let's start with a word we already mentioned. Parameter. Where's the stress there?
It's on that second syllable. T-ram-tr. That rhythm, T-ram-tr, is key.
Got it. And the action you took at the very beginning, calculated.
Here the stress is on the first syllable. CL-hulated. And you want to link those last 2 sounds smoothly. CL-hulated.
A clear stress really communicates confidence, doesn't it?
It does. Now, for the instruments, this is important because they sound similar. The one you use is the potentiostat.
Potentiostat.
Potentiostat, stress on 10.
Okay. And the other one, the one that often comes up in class materials.
The potentiometer. And that one has a different stress pattern entirely. Potentie is AH.
Potentie AH meter. Ah, the stress shifts to the AH.
Exactly. Just practicing those distinct rhythms makes these long words feel much more natural to say.
So we've gone through the micro-level details, the language, the instruments. Let's zoom out. What does all this incredibly focused work mean for Biosense and for your European project? What's the big picture?
The big picture is everything. This work is part of a major European project to create sensors that can detect different pesticides in water.
And using electrochemical deposition, making the material right there on the electrode, that's the key innovation, isn't it? It solves the stability problem.
It solves the biggest problem for these kinds of sensors. If you just make the nanomaterials in a beaker and then try to, drop them onto the sensor,
They could just wash away.
they could wash away or deteriorate when they hit the water. It's not a robust method.
But by using electrical energy to build the zinc oxide right into the sensor.
It becomes integrated, it's adherent, it's stable, it's robust.
But the trade-off, as you've shown us,
Yeah.
is that you get that robustness in exchange for intense complexity.
A lot of complexity. You have to optimize all those factors, potential, time, pH, all at the same time, to ensure the material is consistent every single time.
Because in sensing, reproducibility is king.
It is. If your nanomaterials are a slightly different size or shape on one sensor compared to the next, your calibration is useless. You can't trust the results.
So that need for consistency is what connects your amazing materials science directly to the real-world goal of environmental monitoring, to the heart of Biosense's mission.
It absolutely is. The rigor of your electrochemistry is what will make that sensor reliable out in the field.
Zorica, this has been fantastic. We've covered so much ground today, from that initial mountain of prep work all the way to the big picture environmental goals.
We really have. We looked at the language for your workload, a lot to get done, the clarity of making a choice with rather than, and the precision of defining relationships with respect to.
And we also talked about using natural conversational words like tricky for a complex problem. And we worked on the flow of your presentation with after that, not to mention all that pronunciation practice.
The vocabulary,
Yeah.
calculated parameter, precursor, and of course, the big two, potentiostat and potentiometer.
So before we sign off, we want to leave you with one final provocative thought to consider.
Given that absolute need for consistency, making sure the material properties are identical every single time, and the challenge of juggling pH, time, and potential, what do you think is the single most critical, non-negotiable parameter for turning this lab method into a truly scalable environmental sensor?
Is it achieving maximum stability above all else?
Mm.
Is it perfect consistency of size? Or is it finding a process where the pH is the easiest to maintain?
That's the question that really gets at the heart of translating brilliant research into a viable technology.
Something to think about. Keep asking those big questions, Zorica, and keep using these English phrases to share your incredible work at Biosense.
We can't wait to dive into your next set of findings. Farewell for now.